And good afternoon, everyone. Thanks for joining us. My name is Zach. I'm the ATS National Sales Manager for Canada and also managing part of our US team these days. In case you are unfamiliar and this is your first time joining us, ATS University is where we kind of dive into some of the sponsors and applications that are focused on in the ATS spec tool. For if you are unaware of the ATS spec tool, it is a free product selection software that helps you as an architect or engineer configure, select, and then download your product details in a number of different formats. Some might be a submittal type format, others might be like a Revit file, or if you need written specs, fixture schedules, drainage schedules, anything like that. All those formats are available for download after you've configured and selected your product. We are sponsored by a number of great manufacturers, one of which is SMS. And today we are going to be diving into trap primers and water hammer arrestors with one of my favorite colleagues in the industry, Owen Dwyer, who's done a number of presentations with me over the, I won't say how many years that we've been doing this now, but a long time. A lot of great partners and presentations together over the years. A couple of bits of housekeeping. This is going to be recorded, so we do have everyone muted upon entry. At the end of the presentation, if we have a little bit of time, I'll show you how you can find those previous recordings on the ATS spec tool. As well, we will be issuing a certificate of attendance, so if you need to self-report the presentation for any of your hours towards your professional development, you can certainly do so. I don't believe this is an ASPE accredited CEU. This is going to be a little bit more, it will be slightly branded as we want to get deep into the actual functionality and specifics of the product. So it's not a generic bland presentation. This is going to be detailed and hopefully help everyone with some practical applications. Which of course, if you have questions along the way, please feel free to raise them. I'll be keeping an eye on the chat and I'll bring them up to Owen as we go. For instance, I already saw there was a couple of questions for when we get to water hammer arrestors, some specific applications that they're looking for feedback on, and we're certainly happy to help. Without any further ado, I'll pass it over to you, Owen. Thanks for joining us again.
Hey, no worries. Thanks, Zach, for the intro. For those that don't know me, Owen Dwyer, I'm the National Sales Manager for SMS, Smiley McAdam Summerlin, out of Whitby, Ontario. I'm also the current chapter president for the Greater Toronto Area ASPE chapter. Those that are not members, if you have any questions on the ASPE side of things, by all means, reach out to me or send Zach a quick message, whatever's convenient for you. My background, I've been with IPEX for 15 years prior to SMS now for about 11 years. And prior to that, my education is in biology research. So finished biology research and I'm in the plumbing industry. So anyhow, today's presentation, Zach, you mentioned was a little bit because of the branding, but as an ATS member and president, I try to always keep my presentations educational. So this is not going to be a sales pitch. I want everybody that's watching to come away with something that they weren't aware of, or to have a more higher level of comfort in their specification of trap primers and water hammer arrestors.
That's a great point. I was mainly talking to the CU side because I know those have to be non-branded. But yeah, I know doing presentations with you, we'll certainly probably use, say, the SMS models as the basis just so that we can explain it. But I'm sure the content will cover all types of manufacturers.
Yeah, the content is generic, and because of the pictures that I use, instead of trying to track down copyright and whatever, it's generic. It's not generic in that sense, but anyhow, moving on. So first glitch, can't advance the screens. All right, so we've talked about the introduction of what SMS does. I'll go through shortly, but it's going to be in reference to the national code, because not only do we have people here from Ontario, I'm assuming, Zach, this was opened up to all of your ATS members across the country. So everything is verbatim that I'm talking to. The only difference in references would be Part 7 versus Part 2 in the national. We're going to talk pressure drop, flow through, and electronic trap primers. Quick overview and touching on some of the features and benefits of each. We're going to do an analysis as to mainly trying to focus on electronic trap primers versus the older technologies. And then we're going to get into water hammer arrestors, sizing and placement as per PDI recommendations and industry practice, and then a quick summary. So I won't go too much into SMS. We're unique in the sense that we're set up nationally across Canada with respect to responsibilities for specific manufacturers, IPEX, SHOT, PPP, etc. So we have a unique approach in our market that we're not. It's not necessarily commodities. It's focused on ICI, institutional, commercial, and laboratory type of projects. A quick line card shot. Again, you can see on the left-hand side is predominantly corrosive waste. We do the PPP across Canada, as well as identification systems, valve tagging, access doors, stainless steel drains for food and beverage, dairy, brewery, and as well as modular seals for below grade or sound vibration isolation, etc. So what does our code say with respect to trap primers? As I mentioned in the national code, it's 24551. In our provincial code here, it's part 2 is part 7. So it states, a provision shall be made for maintaining the trap seal of a floor drain by A, the use of a trap seal primer, B, using the drain as a receptacle for an indirectly connected drinking fountain, or C, other equally effective means. So on the right-hand side, that is you can see 24551 on the right-hand side. It's verbatim in Ontario. So products, you have pressure drop primers. You have electronic trap primers. You have flow-through primers and other equally effective means. You can see that there's the vegetable oil. I'll talk about the vegetable oil in a minute, of which the latter equally effective means I'm not a fan of, but we can discuss that. And I'll just tell you what that is here in this next slide. So what are equally effective means? Let's address that first off. You have a trap. So to maintain the trap seal. So as we know, a P-trap, the purpose of a P-trap is to prevent gases, noxious gases from your sewer coming back into the occupied space. And that's done by way of a trap. You have your top crown, your trap arm, and that water, you can see that seal in that image there on the bottom left. That is your trap seal. That is sealing. It is a water seal that's preventing the sewer gases from coming back into the occupied space. So these devices, as we're all familiar with, you have multiple manufacturers that offer these insert type seal products. If we're going to be specifying those as a means of trap seal priming or trap sealing, why don't we just eliminate the P-trap altogether? Because we can't. As part of our code, we need the P-trap. And the reason the P-trap is there is the bottom left side. It is to create a trap of liquid water seal. And I don't know if you may know, sometimes in school boards or other facilities where they have a drain that is out in the back 40 somewhere that's very rarely used. That's the old plumber's trick, is to pour vegetable oil down the drain because it's not toxic, but at the same time, it doesn't have the same rate of evaporation as water. So they would go back, and if they have a stinky drain issue, they just throw some vegetable oil down the drain, and it buys them some time. So let's talk about the devices first. So pressure drop primers. A pressure drop primer needs exactly that. It needs either a 3 or 10 psi pressure drop in line pressure. Different manufacturers offer as low as 3 psi. I haven't seen anything lower than 3 psi. But when they first came out in the industry, 10 psi was the norm. They've become a little bit more sensitive to that 3 psi pressure drop mark over the years. So essentially what they do is they automatically prime either 1 or to 4 floor drains using a distribution cup on the bottom. So when it's activated and it senses that 3 to 5 psi pressure drop, it releases um, uh, a bit of water. Sometimes they're drips, sometimes it's a solid stream during or throughout that duration of pressure change within that range of 3 to 10 psi. So essentially, a valve operates between that 20 to 80 psi range, and typically there's no springs or diaphragms or plastic parts. They look like this. Again, this is a PPP image, but MyFab, Suchi, there's a whole bunch of manufacturers that look almost identical to that. And their typical installation is depicted there. That comes with most of those devices. That debris loop, that is an important part of the proper installation of these pressure drop primers. What that is doing is it's taking off the top of the supply line and 90ing down to a valve. And why that is because the top of that pressure drop primer is a very small orifice. That small orifice can be very easily plugged with any type of debris, something that becomes dislodged in the system, be it a buildup of mineral, be it solder, whatever's floating around in that piping system. If your takeoff is below, it's more apt to become an issue versus taking it off the top.
And just a quick question as we continue on through pressure drop. One thing you mentioned there, the 3 to 10 psi drop, the primer is working only during that drop, right? It's not like that drop triggers a set amount of time, correct?
Correct. If your static line pressure is 70 psi and an adjacent fixture activates, be it a flush valve and whatnot, as long as, depending on which device is installed, if it goes from 70 to 67 or below, it will activate during that drop in pressure. Same thing for the 10, but the 10 would need to go from 70 to 60 or below to activate properly. So this is the typical installation as I showed in that picture. You have your device that is kind of like a piston style, and I don't know what magic happens. My understanding is there is an O-ring in there that has a seal, and that seal is set to withstand a certain amount of differential pressure between the set line pressure side and the atmospheric side, and it basically trickles water past it at that set. So basically, to get to the 3 psi, think of the analogy of making that gasket or that O-ring seal a little thinner versus the 10 psi, which would be a little bit more robust of an O-ring. So you have your cold water supply, you've got your check valve seal, your vacuum breaker ports, we'll talk about shortly. A note worth pointing out here is that for a minimum code requirement or manufacturer's recommendation is an elevation of a minimum of 12 inches above the finished floor. You want to have enough gravity flow to your drain. It can't be right on the floor. It's just not enough head pressure, if you will, to drive that prescribed dosage of water that's going to be coming out of that unit to reach the drain. And typically, it's for every 12 inches of elevation above finished floor, you get 20 linear feet of primer piping. So if your drain is 30 feet away, you might want to put that trap primer a minimum of 36 inches to make sure that you've got, what did I say, 30 feet? So you would have it 2 feet, 24 inches above your finished grade. Vacuum breaker ports we talked about, and that's the actual priming valve itself that we can see. And I'll talk about this installation with or without the distribution cup shortly. So as a standalone, without the distribution cup, it's priming one drain. With the distribution cup, you're going to be able to spread that water flow throughout multiple drains. So just a quick advantages. Pressure drop primer, they're easy and cost effective to install. They've been around for a long time, and when installed properly under the right conditions, they perform as expected. It's not, again, there's perfect applications for them, and we'll go through that shortly. But when they're installed properly under the right conditions, they perform as expected. They can do up to 4 drains, as I mentioned. However, they are not suitable for low flow fixture or booster pump scenarios because of that 3 to 10 psi pressure range. If it's not seeing a sustained pressure drop for that period of time, it might get down to 3 or 10 psi below static line pressure, but a booster pump kicks in 5 seconds later, and you don't have enough of that sustained pressure drop for the device to activate. So it is not a fault of the device. They are older technologies. Typically, when we had flushing or fixtures, they were not as water conscious as they are today. So based on our water consciousness today in today's devices, sometimes these pressure drop primers are not the right choice as a pressure drop, as a priming device. They're not water conscious, so basically they flush for the duration of that pressure drop. So if you have a facility where you have quite a lot of usage of those fixture groups, toilets, urinals, labs, etc., you have already replenished the evaporated water in your P-trap. Everything else is basically water down the drain, if you will. So again, they're older technology that aren't suitable for the majority of current projects, and we'll explain that a little further. Flow activate.
Quick
Yep.
question coming in here on
Yep.
a bit of a unique application, I think. But they're wondering whether or not this could be used in like a trench drain area. And specifically, could it be installed at the high end of a trench drain and then be activated by the pressure drop at the inlet to the sewer piping?
I would say not the pressure drop primers because of the amount of prescribed water. If you look at the details from any manufacturer, it's small amounts, it's in ounces. So I think if you want to make sure your trench drain is flushed, you might want to go with electronic, and the electronic could be set on a prescribed flushing cycle for, depending on the amount of debris that needs to be flush down that trench. I would not use a pressure drop primer because there's just not enough flow.
Yeah, I would think something like either an electronic or even just up to a solenoid with a DCW probably would work a little bit better. But some variation of that probably is a more akin to what you're looking for in that application.
Right. Okay, so flow activated. Flow activated, unlike pressure drop primers, have no direct relation to pressure, but they do have a requirement for an activation of some sort. So whenever a faucet or fixture is activated for the cold water, be it a tap or flush valve, etc., the unit receives water flowing through it, and there is a prescribed amount of water going down into the floor drain. So you can see this is an example with a directional flow arrow, and it's going from flow direction from right to left. Downstream on the left-hand side, you would have your faucet or your flush valve or whatever it is it's connected to. And again, it will emit the fresh water as long as that fixture is in use. So school application, cold water is left on in that sink. Not only do you have it going down the sink, but it'll continuously run in the floor drain as well. Same thing if you have a flush valve that sticks open, same thing. So not only is it being wasted down the faucet drain, it's also being wasted down that floor drain as well. So as long as that fixture has cold water flow through it, it will continue to have flow through that primer device. And again, they have minimum discharge rates, 5 seconds at 20 psi for 0.845 ounces. So you can see how small volume of water is going through them for a 5-second cold water activation. And again, if it's an 80 psi line, it's 1.65. So similar to the previous question with respect to flushing a trench drain, there's just not enough water for 5 seconds of flow being pushed through it. You're only going to get 1.65 ounces of fluid. So again, as a recap, these aren't, again, it's not rocket science. They don't require pressure drop. They are activated by flow. They are quite cost effective. They're a little bit more money than the pressure drop primers, but again, they're not water conscious. Sometimes you can get them in chrome. They can go right underneath the lab in an accessible cabinet area, but that's essentially their use. They're activated every time a fixture downstream of that faucet is used. So this is going to be talking about back siphonage, and I added this, Zach, to the presentation that I originally submitted because it's important to note that the air gaps that are provided, or the air holes in Canada, are not a permissible form of back siphonage prevention. So these ports are not acceptable as a standalone air gap as per our code requirements. So you would have to have an air gap device in conjunction. So not, sorry, the image is upside down there. My apologies. The air gap should be below the trap primer device, as you can see on the line drawing, because it requires a 1 inch or 2 times the diameter of the supply size as an air gap device. So the image on the right is a typical installation that you would see. If you want to be code compliant as far as back siphonage, you'd need an air gap device in conjunction with that prep, be it a flow through or a pressure drop primer. So I don't know if that's new news, but just so everyone is aware, that pressure drop primer or that flow through primer, whenever you see those little ports on the side, they are intended for back siphonage prevention, but they are not code compliant for back siphonage prevention. They do not fit the definition of an air gap as far as back siphonage. So going on to the third, so we covered.
One quick question there. So
Yeah.
is that something that's commonly an option on one of those flow activated or pressure drop activated trap seal primers? Or is that something that a contractor is going to get from, say, the pipe manufacturer or something like that?
Good question. They should be specified with back siphonage because it is a requirement on the specification side for the prevention of back siphonage, and whatever methodology is suitable for that environment or for that back siphonage potential happening. It's different from facility to facility depending on how many drains are being serviced. So you can put in RPs, DCs, air gaps, atmospheric vacuum breakers. There's a whole slew of different devices. But for the most part, going back to this image here on the right that has the cross through, that is not code compliant as a standalone priming device because of the back siphonage requirement, unless that facility or that zone already has zone protection, then this would be applicable. However, if it requires its standalone back siphonage, you have to put an air gap with that.
Which, just in terms of a quick plug, I do believe we have a backflow presentation coming in, I think it's next quarter. So if you want to learn more about zone isolation, premise isolation, and your point of use isolation, certainly jump on that. Because I would imagine, yeah, like you could have this air gap type vacuum to prevent your back siphonage, or if this is for a parking area and you're protecting the entire parking area with a small RPZ or DC DVA, depending on your application.
Correct.
There's lots of different ways that you can go about it.
Right, exactly. So this, if it is a standalone trap primer with no other upstream zone protection, you have to offer zone protection because a floor drain is considered a severe hazard.
Yeah. And then we just had a question coming in, so probably good just to reiterate it. Do we have to specify the air gap accessory when we specify a flow activated or pressure drop activated primer,
You
or
should.
does it automatically come with it?
You should. It doesn't automatically come with it. They are two separate products. A lot of times, an inspector, the inspector has seen so many of the wrong installations that they think the installation is right. So I'm not blaming anybody, but because it's been happening for decades and being installed improperly doesn't mean we should continue to do it improperly. So it should have an air gap in them. They do not come as an assembled component. So moving on into electronic trap primers. Electronic trap primers are exactly that. They use power, be it 120 volt, 12 volt, or 24 VAC. They can do up to multiple drains, up to 4 to 30 is typical. I have never seen a manufacturer do more than 30, either flush mounted on the wall or recessed into the wall. All of them feature an atmospheric vacuum breaker, which we'll touch on shortly. A preset infinitely adjustable recycle timer is what you're looking for. Not all electronic trap primers are created equal. They should have a manual override or a test button just to make sure that the device and the solenoid are acting properly. Again, as I mentioned, various voltage, whether it's 120, 220, whether you have a battery operated unit at 12 volts or a BAS system that's operating at 24 VAC. They are calibrated manifolds. So typically you have water that's coming in and it's not a full port because your first drain is going to see the predominant volume flow, second drain less, third drain even less, et cetera, et cetera. So these manifolds are calibrated, so they're not full port. If you ever tip one of those manifolds upside down and you looked in, they have an orifice inside the outlet to accommodate a equal flow distribution through those manifolds. Typical either 5/8 or half-inch compression on the outlets. That would be the difference between either a rigid copper or a soft copper or a poly tubing on the half-inch OD compression, which is typically 3/8 tubing. So before I get to the next point, there's also now, because of popular demand, half-inch PEX and half-inch PEX 19 or Pro PEX connections in lieu of the half-inch or 5/8 compression. Pricing typically doesn't change. It's just a matter of the contractor ordering at that time what the connection type is. Electronic trap primers are extremely water conscious. We'll go through that in detail here shortly. But electronic trap primers are also available in, again, these are trade names from PPP, but other manufacturers have ones that are similar. So instead of a cabinet, these are kind of like the plug and play or hardwired guys. Some of them have no timers and they require activation through a BAS. So there's multiple variations of electronic trap primers, some of them, again, with the little sub-miniature solenoids, and some that require activation by BAS, with or without boxes and cabinets, etc. So they come in all different shapes and sizes. So you can see up here, for example, these two have a air gap, and the solenoid is activating as the priming device. Whether the top image there, it's hardwired to a BAS, solenoid opens, air flows through the air gap, and that is protected against back siphonage. And the bottom one there with the box, again, that would be a hardwired unit. Again, similar scenario. The solenoid valve would open. That is your priming source of water, and then you have your air gap and a distribution unit for your back siphonage protection. And I mentioned they can do up to 30 drains in one prescribed dosage or activation. And depending on the model size and the drains primed, the initial capital cost is going to look higher because obviously you've got more bells and whistles, you've got solenoids, electronic components, etc. But again, in the end, extreme water conservation is key for these units. So just a little preamble on what this, I'm making a joke here. This is a highly scientific pressure drop to electronic trap primer comparison. So what we did, we took a scenario using our region of Durham, where our office is in Ontario. We took our bulk water consumption rates and the flushing frequency of a pressure drop or flow activated primer with similar use. In a the general intent is to just illustrate the benefits of an electronic trap primer over pressure drop or flow through. So in general, we have a building that requires priming of 30 drains. So the quantity and configure of both pressure drop and electronic primers were selected to suit that scenario. Just take a plan. Here's where your drains are for a basic typical comparison. So in that, we're going to take a high volume of flow. We're going to take airports, an arena, a casino, a mall, somewhere where you've got high fixture usage, and basically a tremendous washroom usage and activation. So first priming scenario, you're going to take 15 pressure drop primers. Again, this is using nomenclature from PPP. Could be any manufacturer, be it 3 to 10 psi. Plug in the name, and based on the scenario, we're going to take 15 of those pressure drop units with a distribution cup, and we're going to have 200 flush times a day for 30-second cycles, delivering approximately 15 ounces per cycle at a 75 psi inlet pressure. Versus electronic. So now we've selected, one 20 outlet station and one 10 outlet station in different parts of the building to accommodate those 30 drains. And again, these are electronically activated solenoids and factory settings, typically 6 seconds to deliver approximately 10 ounces of water per port at 75 psi. So again, all parameters equal. When you start to look at your water consumption, this is where the eyes should get opened. So 15 pressure drop primers that deliver 15 ounces per cycle, 200 cycles per day, every day of the year. Again, this is just picking extreme type of scenarios. That is 16,425 ounces, or 160, or divided, by 160 to get gallons, 102,000 gallons a year to prime floor drains. So, and again, I know this is an extreme scenario, but it's just for visualization purposes. So again, this is going back to our first block water rate usage here in Durham for cubic meters. For the first 1,000 gallons is $4.29. And then the average sewer rate is $1.60 per cubic meter at first block rate. Annual sewer and water consumption for this facility would equate to about $1,200 in water usage for drains, essentially water down the drain to keep these trap primers functioning properly. Versus you have a 20 and a 10 electronic trap primer, 30 ports, 10 ounces per day, 365 days a year. You have 109,500 ounces divided by 60 gives you approximately 684 gallons per year. So its total annual water sewage consumption is $7.92. So these have increased since I did these calculations a few years back. But again, it's just a matter of a visualization of the benefits of electronic trap primers over pressure drop, because every time there's a pressure drop, if they're installed in the right environment, every time there's a pressure drop or every time there's a flow through, there's a prescribed amount of water. Whereas electronic, it's once a day for a set period of time. And again, just standalone cost comparison on water consumption is worth noting.
That volume always throws me for a loop. Like the amount of water that goes into activating those flow through or pressure drop activated, because it's every flush valve activation, right? Like that's basically what it is.
Every time
flush valve drops the pressure enough to activate the pressure cycle.
correct. Yeah,
It's a wild amount of water. And I would imagine, I know when you put these calculations together, and I'm sure that over the last handful of years, those prices
those numbers are higher.
They're
Yeah,
not
those numbers are higher for sure.
Yeah.
But again, the ratio would be the same. So regardless of the cost of the water consumption, the ratio would be uh, comparable. So just a quick capital approximate cost analysis. Again, these prices have changed, but again, it's for kind of analyzing if you're going to sit there and look at cost comparisons. So 15 of those pressure drop primers, let's call it $965 for a wholesaler or contractor. Distribution units, you're going to need 15 of those as well. 15 labor units at $80, 2 hours per install because you're sweating in if you're doing it all properly. So you've got a total install cost of $3,852. The cost of a PT10. So again, you have initial sticker shock from a lot of people, $1,100. It's going to take about 3 hours to install that. And then you've got a PT20, it's $1,309, and it's going to take approximately 4 hours to install that. And then you have to take into account the different trade for running the electrical. And again, this is not something that we made up. We had a contractor do this analysis with us to give us some fair results. So as you can see, the installed cost for the material itself as well and the labor to install them, even if it was negligible, the cost and water savings should be the selling factor. But a lot of times there's people, they get a sticker shock because, okay, it's going to cost me $2,400 for these electronic units, but it's only going to cost me, half of that for doing a pressure drop. But by the time you actually install them, it's cheaper to go electronic. So in our analysis, electronic priming proves to be 1/150th of the water and associated consumption costs per year. And electronic priming proves to be a lower overall capital cost and instant payback, even if those were a wash. And there is no instant payback. The payback is coming in the water conservation, the benefits of providing and keeping with the objectives of LEED. And we recommend specifying electronic trap priming to the maximum extent possible for multiple factors. One, water conservation. Two, low flow. A lot of days today we have low flow faucets, low flow everything, and we're trying to conserve water. And then you have a facility that has not only low flow devices, but then they add booster pumps. So all of those factors work against flow activated, especially pressure drop primers. So in summary, you have to seal that P-trap that's in the drain and that floor drain. You have three available options, either your pressure drop, flow activated, or electronic. You have, it's good engineering practice that you shouldn't rely on other equally effective means, as I mentioned. No, you don't want to have somebody install that device and that device gets blocked or removed, or you don't want to have somebody going to put vegetable oil down the drain. Take into consideration your flow, booster pumps, frequency of use, etc., and to review and discuss actual worst case scenario projects like we just went through. So I'm going to jump into, and this was one of those kind of pay now or pay later scenarios. So a lot of times if a building owner is looking, wow, like a contractor submitted this, it's going to cost me $1,200 to put in pressure drop primers. And, why are we specifying electronic? You could say, well, pay now or pay later. So what you're going to be doing is you're going to be paying quite a substantial amount more in your water and sewer consumption, Mr. Building Owner, going that route.
Yeah, and while you get over to that other part for the water hammer arrestors, a couple of questions coming in.
Sure.
One, I guess just maybe you can comment briefly. I know we kind of talked about it in terms of low flow world and low flow fixtures affecting the choice of priming.
Right.
I would mention that historically there had been almost a direct hardwired or direct connection to the vacuum breaker tube, so that when you flush the toilet, there would be an amount of water that's going down that tube and lead to your trap.
Right.
With the low flow world and the fixtures that we're in, that sort of method worked okay when we were doing 3.5 gallons. When 1.6 gallons per flush was your low flow, that was okay. We had an allowable amount of water that we could divert and not affect the performance of the fixture. these days, when you're down to 1.28 is your low flow, we're seeing 1.1, 1.0 gallon per flush as your ultra low flow. There's not a lot of water that you can afford to divert and still flush effectively. I don't know
Right.
if you have any additional comments on that.
The only additional comments is duration of pressure drop as well. So in those extremely low flow, if you do have a pressure drop primer that is on the lower end, like that 3 psi pressure drop range, it's only going to activate for the amount of time that that ultra low flow fixture, if the installed scenario is if all of those stars aligned, you're only talking a very small amount of water. So.
And then another question coming in just on that cost breakdown analysis that you had brought up. Question on whether or not there's additional piping that would also affect that install cost.
It's a good question. I don't know if that analysis took that into consideration, but if you have 30 drains and you have a minimum elevation of 12, let's say it's at the 12-inch mark or up to 60-inch mark, if you will, for an electronic install. I don't think the piping would come into play because you still service the same amount of drains.
There
However,
likely would be some additional piping in the trap seal because you're centralizing your distribution. So you're not going to have your distribution as close to the drain as, say, where your flow or pressure-based drop would be.
right.
So there's likely a minimal, there would be some additional piping that I think would be incorporated. Yeah.
Yeah,
But
and
at the same
it's a
time,
good
it's
point.
also easier to install, when
Yeah.
you're, because they hit earlier in the layout.
And one point to note too, on all flow through or pressure drop primers, their connection size is 1/2 inch, whereas an electronic trap primer is 3/4 inch. So that's something to consider as well. So your piping diameter connection on your electronic trap primers is 3/4, not 1/2. So, and again, that analysis was not taken into consideration. It was more of a comparison of water consumption versus, the labor to install and whatnot. So yeah, there might be negligible um, differences with respect to piping costs, but again, it was
Good
more
point.
so.
Always good to consider all the different aspects that can affect it. In my experience, I think it would be probably negligible and not affect your cost benefit analysis, but worth considering certainly. All right,
One
let's
thing,
jump into water.
yeah, one thing to note, and just again for sake of time, I did want to touch on it because it is important. For those that are in the know or have been asked by a local inspector with respect to an atmospheric vacuum breaker in an electronic trap primer device. Historically speaking, and CSA B64 had tagged or flagged or classified floor drains as a severe hazard, as we mentioned. And atmospheric vacuum breakers were not permitted without additional zone protection to be used in a severe hazard application. CSA has amended their CSA B64 and they have removed that asterisk. If those that are interested and want some more information, again, just for sake of time, atmospheric vacuum breakers and electronic trap primers are now an acceptable back siphonage device in electronic trap primers, and they do not need additional zone protection.
And just before we dive into this, I'm going to bring up the question that was raised before we started, and maybe during the present, we don't have to answer it now, but as we go through, just keep it in mind. They had a question about a particular installation. Why would an overhead water hammer arrestor be making noises when the bathroom's in use? There's 2 bathrooms, each with a WC and a lav. Each bathroom has their own water hammer arrestors. So I guess when we get to the sizing aspect, maybe we bring that up then.
Yeah, we'll go through that. And again, this is based on PDI and this is based on industry practice. Sometimes these need to be looked at in like an industrial process application with a little bit more intent and design. But this is basically, that's why I'm saying it, this is the concept. So to convey the concept of water hammer arrestors, where to put them, the size, general sizing, etc. So the concept, water hammer arrestors. So what is water hammer arrestor? We're going to talk about identifying water hammer and the reasons to fix it. So damage to fixtures and fittings. So by definition, the term is used to define the destructive forces, pounding noises, vibration, anything that develop in a piping system, where a column of non-compressible liquid is flowing through a pipeline and stopped abruptly. So how that happens is solenoids, opening and closing of valves, et cetera, et cetera. So those forces have been known to generate um, upwards of explosive potentials. We're going to go through that a little bit, but the forces generated at the point of stoppage can be compared in effect, as I mentioned, to that of an explosion. So water hammer arrestors are needed for this reason. Water hammer occurs when a high intensity pressure wave travels back through the piping system until it reaches the point of relief, such as a larger diameter of pipe, as the riser, etc. That shock wave will then surge back and forth between those two pipe reliefs and the point of impact until that destructive energy has been dissipated or absorbed. That violent action accounts for the piping noise and vibration, and the faster the water flows through the system, the more intense that water hammer or that noise will be. So we're increasing the possibility of damage. So just a kind of line drawing of what's happening. So you have a closed system, water is static, opens abruptly, that water is now flowing, and then again it closes abruptly, and then you have that sudden shock. So that shock goes not only forward, but now you have it coming back on itself, and that those two flow joints, that conjuncture, is where you get that energy. So the absence of noise, it's important to note, does not indicate that the water hammer or that shock doesn't exist in that distribution system. Sometimes it's mitigated by the material of the water supply, like PEX piping, for example. If the piping has the ability to move, it might absorb that shock, whereas a static, like a more rigid piping system. So the resultant water hammer shock travels back and forth in the piping, as I mentioned, between the points of quick closure and the point of relief at a rate of 4,000 to 4,500 feet per second. So that shock wave alternatively expands and contracts that pressure during this occurrence, and that destructive force can cause the following conditions. Obviously, ruptured pipe, leaks, leaking connections. It can weaken those connections if you've got a thread-to-thread connection. You've got a mechanical joint between dissimilar materials. Again, as we're all aware, there was vibration and noise, damage to those valves back and forth. Again, damages to all kinds of valves, meters, gauges, any kind of recording apparatus that has a maximum PSI requirement. So it could loosen pipe hangers. It could cause premature failure of other equipment and devices within that system. So it needs to be something that's looked at and addressed. And as I mentioned, these are your main culprits. So any fast closing valve, any pressures and spike. So for example, like system interruptions. So, okay, we had a power outage. Now when the power comes back on, everything just opens up again and there's no slow ramp ups. Pumps again are sources of that shock. So the means of control, water hammer arrestors. So you're trying to include a device in your system that acts as a shock absorber, if you will, for that shock that's being generated by that slow closing, sorry, that fast closing device. So PPP, it's their SC series. Other manufacturers have their different series, but essentially what you have is this. It's an air chamber. So old school shower valves, for example, used to have two pieces of pipe extended with caps on the top, and those, as you fill your system, would be the homemade water hammer arrestors because it had this column of air. And as we know, air is compressible, fluid isn't. That is the principle behind these, where you have a trapped volume of air in those devices. As the water hammer or that shock wave is coming in, you have that piston. So you can see in the cutout there, it's a double O-ring piston that will push in and compress the air, and that air again will compress. So the pressure within that chamber is going to expand quite a bit, but it's that cushion effect that allows for that absorption of the shock. And there's different types, but to go back to the analogy of the PEX or the copper lines at the shower valve, what happens over time is air is reabsorbed into that water system, and eventually that your tubes become full of water anyways. There's no longer any air because the air will redissolve. These systems are separate. However, if you do have a piston style arrestor like this that is subjected to above and beyond its prescribed pressure, you might have that air leaking out and rendering your device useless if it hasn't been protected during initial startup, or if that pressure has been exceeded, if it's exceeded its capacity. Another type is the bellows type of arrestor, so almost like an accordion. They're designed to operate for domestic and commercial use. They're typically found in a stainless steel type of a format. They look like a mushroom head, but inside you can see the cutaway. It's got that bellows effect where the fluid shock comes in, and that bellows will open and compress again up and down to compensate for that expansion of that shock wave. So during design and construction, water hammer arrestors must have the capacity to control the shock adequately. So undersized ones are going to underperform. They're not going to have enough capacity to manage. So the construction must be of a quality that will enable the unit to provide many years of dependable service. That's the analogy that I talked about. Instead of putting a T in with two pipes going up, that's not the way we want to design water hammer arrestors into a system. As I mentioned again, they will just they're just going to become full of water at some point in their installed life. So over the years, there's been a standardization through members of the Plumbing and Drainage Institute, PDI. They set forth the standard method for sizing and placement. So again, this is not something that I'm coming up with. It's in manuals, the PDI manuals. PDI recommends 7 different size units for the average plumbing system. There are other sizes, but each unit must have a different size and capacity to control the shock in the piping system of varying sizes and scopes. So as I mentioned on the onset, this is not a carte blanche coverage of all scenarios. This is more of a concept type of presentation. How are we doing for time? All right. So in PDI manual, there'll be a list of symbols that denote the range of sizing from water hammer arrestors. So there's either A's or the double A's, etc. But this is essentially what you have: your pipe size and the number of fixture units that it can effectively absorb or take care of. So the cross reference to the PDI is an A, for example, would be your 1/2 inch sizes up to 11 fixture units. 3/4 inch pipe size will do up to 32 fixture units, and that would have a designation of B, or part number -B, or a part number -A, etc. So simple and multiple fixture branches lines is what we're going to talk about here. They have to be handled differently. The method of sizing is based on fixture units. So we're all familiar with fixture units. It's a quick and relatively accurate and well-known way of dealing with not only water distribution sizing, but also in conjunction to water hammer arrestors as well. So I'm not going to talk about the definition of a fixture unit, and we're going to talk about the difference between public and private. So obviously, for obvious reasons, in our charts, in our code, there is 2 different fixture unit counts. One is for public and one is for private, and that's just based on accessibility, how many people are going to be using these devices, etc., in a given day. You might be familiar with these charts. These are your fixture unit charts. You have your public and your private, your cold water and your hot water lines, etc. So I'm going to be referencing these similar charts as we go through. But again, this is in all of our code and PDI manuals, etc., when it comes to fixture units. Here's the meat and potatoes. So sizing and placement. You're calculating your cold water and your hot water fixture units. When you come up with your cold water fixture units, in this example, you've got 2 water closets and 4 labs. Each water closet is going to have their fixture unit count from the previous chart. Labs are going to have a fixture unit based on their previous chart. Come up with your total fixture unit count for the cold water line. you have a total of 22 fixture units. So if I zip back real quick, 22 fixture units, you're going to size a B size, PDI sized B water hammer device to handle that scenario. So that is a multiple lines. So you have one for your A, your cold water, one for your B, which is your cold water, and then you have your hot water side. You only have the 4 labs, 6 fixture units. That's the smallest one, which is the size A. Example 2, sizing and placement. We've got, again, something where you've got water closets, urinals, and labs. You've done your cold water calculation fixture units. You're going to go to your PDI table and choose the appropriate unit for that scenario. Same thing with the hot water branches. You've got just the labs again. It's the small A size because it's only 6 fixture units. And so those are your two units selected. So the location of the water hammer arrestor in examples 1 or 2 only apply to branch lines do not exceed 20 feet in length. So those are smaller lines that start from your horizontal branch line to the last fixture, not to exceed 20 feet. When the branch lines exceed 20 feet, you need to start adding additional water hammer arrestors. So there's the 2 rule that's been established in the placement of water hammer arrestors over the years. And that 2 rule is rule number 1, covers multiple branches up to and not exceeding 20 feet. So if your branch line to your end fixture does not exceed 20 feet, 1 unit, as prescribed by your fixture units, that size of a device, put that in there, you're good to go. Different scenarios, different calculations. I'm not going to go through them all for the sake of time. Up to 20 feet. So up to 20 feet, that's your direct translation, direct placement. Regardless, your fixture unit size quantity will change, and so will your water hammer arrestor, your line sizes, etc. But that's pretty much it for your example of rule number 1. Rule number 2 covers multiple branch lines, which do exceed 20 feet. So anything that's above and beyond the 20-foot mark is you're going to have to start considering. You're going to have to add multiple arrestors. And in this scenario, you've got the top one, for example. My camera is covering, so I cannot see it. I'm going to cover that. So you have the scenario where you've got your cold water lines totaling 44 fixture units, so that you're going to need two B-sized units for your cold water, and 12 fixture units. You're just going to use 2 A-size units. And where those go are, so again, just to talk A and B here. So 44 on the cold water side. If you come back over to here, 44 is your, it's going to be covered with 2 Bs. So B plus B is 64. Because it's the same line size, I need one at about the 20-foot mark and the other one at the end. Same with my A's. Kind of split. You're splitting. So you can see here that there's 4 on the left, 4 on the right. First one in the center of those, and the last one at the end. You're just splitting up your unit. So it's 12, even though 1 unit will cover 12 fixture units, give or take, instead of putting 1 B in there, but because it's longer than 20 feet, you're going to need 2 of them, and you're going to have to split up that water hammer, because again, remember that shock wave isn't stopping where you put your water hammer arrestor. It's going to continue down your piping system. Again, there's practical limits when covering the overall length of the branch line. In remote instances where a very long branch line is involved, water supply is generally fed from some midpoint, as in this example. So maybe in this example on the left-hand side, you're going to have your fixture unit calculation to give you a unit C up to 20 feet. As you can see there from the top example on the right, you would select for 48 fixture units. That falls under that C unit for that one side. And then on the other side, because you've exceeded the requirements of that C, now you're going to use 2 Bs in that line. And again, you're going to try to split that or position them as equally as you can, whatever makes sense. So ideally, the flow pressure in the branch line servicing those fixtures doesn't exceed 55. So pressure reducing valve should be installed to maintain that proper pressure within the system. However, when you do have instances where 65 to 85 psi is noted or is a part of the system, then you have to upsize your water hammer arrestor, and you can refer to the following tables. So, and again, these are recommendations for sizing and placement arrestors based on industry experience and recommendations through PDI. This is not coming directly from Owen Dwyer or PPP. This is based on PDI's experience over the years with respect to sizing and placement. So as per our PDI manuals, water pressure, up to 65 psi. These are your sizes: A, B, C, D, and E. All the way up to a triple F, and I'll explain what that means here shortly. And then you have 65 to 85 psi water hammer arrestors, and you can see from the previous chart, everything is just one. Let's call it one water hammer arrestor size up. So you could see A's, top left AA, go to BB, that 1B at the 1 inch becomes a C, etc. So if your pressure is higher, you need to go to the next arrestor up. So this is important to note. Defining the size and placement of the water hammer arrestors for a single fixture and equipment branch lines are illustrated in the following picture. So for sake of clarity, all the other bells and whistles have been removed. So for example, a single line is different. So the previous examples we saw where you had multiple branches. This is if you have a single branch and single source equipment water shock device, if you will. So you have your pipe size, length of run, you're running at 55 psi, so you don't have to upsize because you're under that 65 psi threshold. Velocity, and your PDI unit recommendation is E. You always want to place your water hammer arrestor as close to the source of shock as possible, be it the pump, be it the solenoid, etc. So you always want to try to put your water hammer arrestor as close as possible, close as reasonably possible to the source of shock. So in that scenario, up to 65 psi, you can see that it was 92 feet, 1 inch line. So you have 92 feet, so let's go to the 100, and it was a 1 inch line. So you've got the E there. And so that's the size that you would choose and place it as close to that equipment with the quick closing valve as you could. Second, for example here, pardon me, your pipeline sizing is 2. You've got 98 feet. So again, your PSI is under that 65 PSI range, so you don't need to upside. So 2 inch, 98 feet, 60 PSI, 2 inch, 98 feet. You're now looking at 2 FF arrestors. So you would put 2 F designated arrestors there. And that's again based on that PDI chart of sizing of the arrestor. Here's another example. So you've got 3/4 inch lines. You've got a cold water and a hot water. Each of them will require a separate line. And again, you've got 3/4, 75 feet, 50 PSI, and below that 65, I'm just going to put the 1 unit. And the biggest difference here, if this was 70 PSI, instead of a C, it would be a D designated unit, because you're going to go 1 size up if your pressures are higher. This is the last kind of line diagram picture I have for you, and one more quick note afterwards. You can see here that the arrestor that's selected is not placed horizontally. It's placed at the change of direction. So if you do have a change of direction, that is, again, you have that quick closing valve on that open side tank, and you've got a 90-degree elbow there. If you take that 90-degree elbow out and change it to a T, that shock wave from your shock source valve up is going to be your best placement scenario for the arresting of that shock wave, as opposed to putting it on the horizontal position. So one thing to note before we open it up to questions, the maximum connection size. So what happens with a water hammer arrestor is the barrel size changes, but the maximum actual threaded or solvent weld or socket weld connection is 1 inch. So if you specified a 2-inch water hammer arrestor, it'll come as a 2-inch barrel sized appropriately for that shock wave, but the connection sizes are always 1 inch. So don't be shocked if you think somebody's supplying you with a 1-inch water hammer arrestor. It's actually 2. The size of the chamber and the air capacity is suitable for the 2-inch water line or for the 2-inch shock line, but the connection sizes max out at 1 unless you go to a flanged connection. So I hope that makes sense. And again, this was kind of a quick flyover concepts of water hammer arrestors. Every scenario was different. If you have any questions, by all means, if I can't answer it, I can always reach out to the engineers at PPP as well. But on that note, I appreciate everybody's time, and I do apologize for talking fast at the end there, but I had more material to cover in a shorter period of time. So.
Yeah, we covered a lot there. Thank you very much for those that have stuck around. I do recognize we're already a couple minutes over the hour, and appreciate those that are able to stick around. Although I understand that other meetings come up and people may even be jumping to another webinar. If this was your first time attending ATS University, thank you very much for joining us. I hope you stick around because I'm going to do the quickest 5-minute intro to where you can find these products that we talked about today on our free ATS spec tool. If you've already attended before and you're familiar with the ATS spec tool, I still encourage you to stick around because I'm going to show you what I think is the coolest new feature that we've launched in the last couple of years. For those that may not be familiar, atsspec.com. Click here to sign up, click here to log in. You'll have a firm-based account so you can share projects and masters within your firm. If you want to review this webinar in the future, you can go to this Architects and Engineers tab, down to our Learning Hub, and over to Webinar Recordings. You'll have access to the presentation and any of our previous presentations. And this is going to get beefed out in the future. We're going to be coming up with a more formal kind of learning program. Some of these products are going to be included in what we call our ATS templates. Templates is, in essence, an application-based master recommended by ATS. You may have your own long-term care standards at your firm. These will likely align or give inspiration or help educate. If you have any questions on these, feel free to reach out to me. I can help advise on the product selection and what goes into them. One thing I did want to show is that we have, for instance, our mechanic room design here, which would, of course, have traps or have drains and funnel floor drains, which would need priming. So we'll show you how to use that in the future. Not only are they available to help educate you on the product selection, they are also available to help enhance and increase the efficiency of your product selection. You can see I'm logged in here now. It tells me I'm logged in as a demo engineer. This is our new dashboard. You can see the presentation today. So we have our dashboard linked in so you can see our upcoming webinars. You can access, download information on the application guides. You can see our great products that we're recommending based on these, educational applications. A trap seal primer, the electronic trap seal primer is a great option for schools because they are often fairly large distances. They often have flush valve application. This is a great product for those applications. New features that we've launched here on our left on our toolbar, we have our product catalog. Now, before you create a project or a spec, you can actually review the product catalog and start selecting your different fixtures. We do recommend still creating a project. This is going to help you organize everything better within your firm. You have projects, masters, ATS templates, and then your quick specs. The difference between a quick spec and a project is the level of detail of the information. If you just put in a quick spec, you can see we've got tests, sinks, faucets. These are single items that you're coming for. We could create one called trap seal primer, ESP. If I just need a quick trap seal primer selection, you can see this takes me back to that category page. You can see I've pinned my favorite categories here where I've got my trap primer. I can click on trap primer, get into this category. I could then filter down by pressure drop or electronic. And then I can find if I'm just doing a small retrofit, maybe I just need the mini prime. Maybe I need a solo prime. It's just for a single floor drain. So I could go solar prime here. I could configure and include the PVC body distribution kit if I need. This is going to help me serve up to floor drains like we talked about. If you want to review the manufacturer's spec sheet to confirm that this is the correct product, hit spec sheet and it'll pop up the manufacturer's spec sheet. These are embedded for every product on the system. And then you just hit add product when you're done configuring. The other piece I want to show is I've got my trap seal and water hammer arrestor webinar here that I prepared as we were getting started for the session. You can see it's completely blank. So envision this is, Owen's building a new, we were talking about the barbershop earlier on. You're building a new barbershop for your brother-in-law, and they need to get a variety of products together. You might want to go through, hit add product, and start configuring, selecting as we go. You might also go to this add from masters and templates, where you can simply drag and drop from your favorite applications. So you can see we've got masters here, we've got ATS templates, then our pin drawings. So if you want to use that mechanical room template that we were talking about, you could search for mechanical. You can see your mechanical room template Canada. If you had a master for the application, let's say you're doing a ton of barbershops, great. You could then find your barbershop. In this case, I'm going to search for that same mechanical room template. And if I've got multiple product groups within this, then I can filter down. If I want, let's do just our trap seal primer first. I'm simply going to drag these dots and drop it over here. Boom, I've selected from my approved master or from the ATS recommended template and copied over the product selection. We talked about, water hammer arrestors and how they, prevent pipes. But if this is a taller building, a different version of that is a pipe support. You might need pipe support. You might need a floor drain in your mechanical room. You might need, let's put another trap seal primer as well. If you got a mop sink in that mechanical room, and then you might need an eye wash, depending on what sort of cleaning chemicals you're using. We were talking about backflow. You might need a backflow preventer for the zone isolation, and even point of entry water filtration. Not to mention your sump pumps that can be sized, or your water heaters that can be sized. I can select these checked off boxes by taking this group here and drop it over. I could also do the entire room and then drag everything over. One of the other great features is you can see I've got something here. We've got our first product group that we started building, and we have add new product group. You might do your fixtures in a new product group. You might do all your drainage in another product group. You can simply drag the same master over to where it says new product group. It'll create a brand new product group with the boxes that you've checked off. Probably my favorite feature that we've launched from ATS in the last 3 to 4 years. It saves me a ton of time every time I'm working on the system. And now I've populated this. If I want to now download this file, I can simply check the box, go to download, and then download it in any one of the free compiled product selections that we've mentioned before. If you need Revit files, the manufacturer specs, we've got written specs in long, short, and 3-part spec. If you are doing a schedule in Excel and you're putting that schedule directly onto your drawings, you can do so. If you want a pretty picture product brochure, you can check this box and get that. Or our standard ATS submittal, which I imagine most people are probably familiar with. If not, and this is your first time, this is the quickest intro ever. Please reach out to me. I will guarantee you I can give you a more in-depth, better intro to ATS spec tool than what I'm doing today. We would download it and then just take that information, put it into however you are configuring your product solutions. If you are writing a spec, if you are using master spec, if you are using an internal standard written spec, this will give you updated verbiage that you can put into your project package. If you are taking cut sheets and putting on a drawing, at least use a configured cut sheet instead of just the base model that leaves it open to interpretation and allows a contractor to adjust. they could easily skip something like the air gap that we talked about earlier on today with our water hammer arrestors, and this tries to help you. So that's all I have for today. That was my very quick intro to ATS presentation. That was a great detailed presentation on water hammers and trap seal primers. I guarantee you the 50 something people that showed up today, I don't think that they were walking in thinking, hey, I'm going to actually learn something about trap priming today. A lot of people just come in and you're just like, hey, we're here, we're learning, this is great. I always love presentations with you, Owen, because we walk away with practical knowledge that affects your design. So thank you for once again providing great detail
My
and
pleasure.
really giving a great presentation.
Thanks for the invite and the opportunity. Always appreciate it. Thanks, Zach, and all those that are
Absolutely.
still online. Cheers.
Absolutely. Thank you. Bye for now, all.
Take care, guys.